Hello and welcome to this video in which we will continue our theory of polynomials and theory of equations. So we had seen a slide up to 6, that is this slide. We had covered identity theorem and its corollary. By the way, if you are new to the channel, then make sure that you subscribe to the channel for more upcoming videos on algebra, and make sure you press the bell icon as well so that you can get notified about new videos. So with that aside, let's get right into it. So you can find these slides at ashtavalkar.org. You can follow the navigation and you can arrive at these slides. So the second corollary of identity theorem is given here. If fx is a periodic polynomial with some constant period t, that is fx is equal to fx plus t for all x in set of real numbers, then fx is equal to c. So the proof follows that we let f0 is equal to x, then f0 is equal to ft is equal to f2t, and so on is equal to c. Thus polynomials fx and constant polynomials gx is equal to c takes some same values for infinite number of points, hence they must be identical. That is, fx should be equal to gx. Next theorem is rational root theorem. It says that if pq belong to the set of integers q not equal to 0, this equal to is extra, this should be removed, such that they are relatively prime, that is the greatest common divisor of pq is 1, then if p by q is the root of the equation an x to the power n plus n minus 1 x to the power n minus 1 and so on up to a1x plus a0 is equal to 0, where a0, a1 through an minus 1 and an belong to set of integers and an is equal to 0, then p is a divisor of a0 and q that of an. So we are given that p by q is the root of the given polynomial, that is this polynomial. So we substitute this, we get this, and after taking LCM we have n p to the power n plus n minus 1 p to the power n minus 1 q and so on up to a0 q to the power n is equal to 0. So we take n p to the power n to right hand side and divide by q. So we get n minus 1 pn minus 1 plus n minus 1 p to the power n minus 2 q and so on up to a0 q n minus 1, and right hand side we have minus n p to the power n q. Now everything on left hand side is an integer and p q are relatively prime, therefore q must divide n because q will not divide p here, so q will divide n here on right hand side. Similarly, we can prove that a0 is divisible by q by taking a0 qn to the right hand side and then dividing by p. We can prove the relationship like this. The corollary of the above theorem, that is rational root theorem, is integer root theorem. It says that if roots of xn plus an minus 1 x to the power n minus 1 and so on up to a1x plus a0 is equal to 0, where 0 less than equal to I less than equal to n minus 1 are integers and coefficients are also integers, it's repeated, then all the roots divide a0. So this corollary is a direct result from the previous corollary, corollary which we have proven, where p by q is the root of the polynomial. Then similarly we can prove this for integer roots. Next up is Vieta's relations. Vieta's relation says that if alpha 1, alpha 2 and so on up to alpha n are n roots of the equation n x to the power n plus n minus 1 x to the power n minus 1 plus so on plus a1x plus a0 is equal to 0, then sigma I is equal to 0 to n alpha I is equal to minus an minus 1 by n, sigma 1 less than equal to I less than equal to j n alpha I alpha j is equal to an minus 2 by n, sigma 1 less than I less than j less than k less than n alpha I alpha j alpha k, this should be k, is equal to minus a n minus 3 by n and so on, and the product of all the roots would be minus 1 to the power n a0 by an. These relations are also denoted as small sigma 1, sigma 2 and through sigma n as well. These relations are known as Vieta's relations because Vieta gave these relations. So this you can easily prove by mathematical induction. Okay, so you can start with one polynomial x minus alpha, then you can go with x minus alpha, x minus beta for quadratic equation you can prove, and then you can assume for n is equal to m it is true, and then for n is equal to m plus 1 you can prove this. Symmetric functions are functions like a plus b plus c, a square plus b square plus c square, a minus b whole square plus b minus c whole square plus c minus a whole square, and a plus b, b plus c, c plus a, in which the terms can be interchanged without changing the overall function. Functions demonstrating such behavior are known as symmetric functions. They should have been italicized. In general, if a function is of n variables, then this definition warrants that any two variables can be interchanged without changing the function. Thus, we see that Vieta's relations are symmetric functions. So, these relations sigma 1, sigma 2 and sigma n are symmetric relations in this because you can interchange any with any other one. Common roots of polynomial equations. If alpha is a common root of the polynomial equation of x is equal to 0 and gx is equal to 0, if and only if it is a root of HCF of the polynomials fx and gx. The HCF of two polynomials can be found exactly like HCF of two integers using Euclid's methods. Next comes irreducibility of polynomials. So when we talk of irreducibility, we talk in terms of set to which the coefficient of the polynomials belong. This set could be set of rational numbers, set of integers, set of real numbers, or set of complex numbers. A reducible polynomial is a non-constant polynomial which cannot have non-constant factors in the same set as coefficients of the polynomial itself. For example, a square minus 5x plus 6 is x minus 2 into x minus 3. So it is a reducible polynomial in Q, in I, also in Q, also in R, also in Z, also in C. X square minus 4 by 9 is x minus 2 by 3 into x plus 2 by 3. This is reducible in Q, R and C, but not in Z. X square minus 5 is x minus square root of 5 into x plus root 5. This is reducible in R and C, but not in Q and Z. X square plus 9 is x plus 3i into x minus 3i. This is reducible in complex number set, but not in Q, Z and R. So this is how we define the irreducibility of a function. Gauss's lemma says that if a polynomial with integer coefficient is reducible over Q, then it is reducible over Z. Now we come to Eisenstein's irreducibility criteria theorem. It says that we have a polynomial which we normally pick a n x to the power n plus n minus 1 x to the power n minus 1 and so on up to a1x plus a0 with integer coefficients if there exists a prime p such that following three conditions apply. P divides each ai for 0 less than equal to I less than n. P does not divide an and p square does not divide a0. Then fx is irreducible over rational numbers and integers. The proof is a bit involving for this. So first we assume that fx is equal to gx into hx such that gx is equal to bk x to the power k plus bk minus 1 x to the power k minus 1 up to b1x plus b0, and hx is cl x to the power l plus cl minus 1 x to the power l minus 1 and so on up to c1x, there should be an x here, plus c0, where bi and ci both belong to the set of z for all I 0, 1 to up to k and l respectively. Bk is not equal to 0 and cl is not equal to 0. This should be 0. Now k is greater than equal to 1 and l is greater than equal to l is k and l both are greater than equal to 1 and less than equal to n minus 1. Now comparing the leading coefficients on both sides, we have an is equal to bkcl, but we know that p does not divide an, so p cannot divide bkcl. That is, p does not divide bk and p does not divide cl. Similarly, a0 is b0 c0. Now as p divides a0, P square does not divide A0, so we find that P will divide B0, C0. But both P0 and C0 cannot be divided by P. Without loss of generality, we suppose that P divides B0 and P does not divide C0. Suppose I is the smallest index such that Bi is not divisible by P. There is such an index I since P does not divide Bk, where 1 is less than equal to I less than equal to k. Depending on I and k, for I less than equal to k, Ai is equal to Bi C0 plus Bi1 C1 and so on up to B0 Ci. And for I greater than k, Ai is equal to Bi C0 plus Bi1 C1 plus so on up to Bi minus k Ck. Now we have that P divides Ai, and by supposition P divides each one of B0, B1 and Bi minus 1, which implies that P divides Bi C0. But P does not divide C0, which implies P divides Bi, which is a contradiction, and therefore Fx is irreducible. So with this we come to the end of this video. There were quite a few theorems, that's why I'm stopping here to let you understand these carefully and let the material sink into you. In the next video we will study extended Eisenstein's criteria, and we will then move on to quadratic equations. So I hope that you have found this video useful and informative. Please like the video, share it on social media, and make use of the comment box to let me know what you think about it. And thanks a lot for watching. Have a nice day.